This lesson will be on slope fields. So most of Unit 7 is about differential equations, and the second part is about slope fields. So slope fields are representations of the slopes of a differential equation. So if we read through, this is the first page of the packet that I gave you today in class. So it says, many times it is not possible to solve differential equations using integration because of the limited techniques of integration. So we don't know the integral of a product or a quotient or anything more complicated. And as a result, slope fields are a graphical way to help solve differential equations. So a slope field is a sketch of the general solution of a differential equation. It gives us a visual representation of a family of solutions to a differential equation. So if you look on your paper, it says and the equations didn't show up on here, so I'm going to write them. You should have let dy dx is equal to 2x. Okay. So this equation, if we fill in the blank, this equation is the differential equation, or the derivative. And you will be trying to find y graphically, which is the original equation. Right, and since dy dx is equal to 2x, 2x represents the slope of the tangent line. So you have here dy dx is equal to 2x, and 2x represents the slope of the tangent lines. And you can graph the slopes at different values to get an idea of what the original equation would look like. So we're going to fill in this chart to find the slopes at different points and plot the slopes on the grid. So to graph slope fields, we plug in the x and y values into the differential equation, and we draw short line segments like this one that show the slope. And if you have a ruler, it sometimes helps because then we can make the slopes the same at different points. So for example, we did -1, 2. So at -1, 2, I'm going to plug it into dy dx, and how they write it is they put dy dx and they put a bar and they put the point, -1, 2. And the only one we care about is the x because that's the only thing in there. So we get -2. So then at -1, 2, they drew a slope of -2. So I'm going to fill in the rest of the chart. So at dy dx at 0, 2, if I do the point to the right, would equal 2 times 0, which is 0. So this would be 0, and so then at 0, 2, I'm going to draw a slope of 0, which means that it's a horizontal line. And so I'm going to fill in the rest of the chart. You don't have to write this out. You can just do it in your head. So at 1, 2, I would do 2 times 1, which is 2. And at 2, 2, I would do 2 times 2, which is 4. And then these down here have the same x values, which means the slope is going to be exactly the same, because the only thing it depends on is the x in this case. And same thing with this. At 0, 1 and 0, 0, the slope is going to be 0. And at 1, 1 and 1, 0, the slope is going to be 2. And at 2, 1 and 2, 0, the slope is going to be 4. And then I'm going to draw little short segments to represent the slopes. So anytime x is 0, the slope is 0. So I'm going to draw little horizontal lines of the slope of 0. And then whenever it's -1, the slope is -2. So I'm going to make sure that I'm parallel, and this is where a ruler helps, to the segment that's already drawn for -2. And I'm going to do my best. It's a little hard on here. And then at 1, the slope is always 2. So I'm going to draw pretty much the same steepness as this line, but going in the positive direction. And just do your best. Just make sure that your slopes, you can tell if they're negative, positive, or 0. And then if you have a slope of like 1 and 3, just be able to tell which one is steeper. And so then part D, so this is the slope field. Okay, so we drew a slope field. And part D says find an equation for y and then graph multiple solutions for y. And how we do that is we let c be different values and graph those solutions. So if I do what we did last video, we separate our x's and our y's. We integrate both sides. So remember the integral of dy, there's a 1 is y. 2x is x squared plus c. So this is my general equation. So for particular, let's say c is 0, then we would just get x squared. If c is 1, we would get x squared plus 1. And then if we graph different ones, I do that in different quotes. So at 0, I'd have 0, 1. And if I graph it, I follow along the slopes pretty much. And I should get the graph of x squared. And if c is 1, then I would get the graph up here. Okay, and if c was 2, then it would be up here. So what this shows is the family solution. So a slope field shows a general solution for an integration. So we're going to draw slope fields for this. So it says graph the following slope fields and then make observations about each slope field. So if you can pause the video and then try graphing these 3 slope fields like we just did, and then you can check your answers. Okay, so if you drew your 3 slope fields, the first one dy dx is 2, all the slopes should be the same and they should be all parallel with a positive slope of 2. So they're going up, left to right, because it's a positive direction. They should all be the same. So I did my best, but it's kind of hard to do on here. So you can see that, and if we do an observation, we can say that all the slopes are equal. And that makes sense since we get a constant value. And if we looked at the original equation would be linear, which we can tell that if we drew in the original equation, you would pretty much have a line if you followed along the slopes. For b, we get x plus 1, and the slopes just depend on the x values. So we can see that when we have an x value the same, all the slopes are the same. So when x is -1, the slope was 0. When x is -2, we get a slope of -1. When x is 0, we get a slope of 1. And then at 2, or at 1, it's 2, and at 2, it's 3. So they keep getting steeper as we go to the right, and they keep getting more negative as we go to the left. Okay? And we can see that if we traced along, if we would draw the original equation, the original solution would make a parabola. Which makes sense because if we integrated this, we would get x squared plus 2x, which is a quadratic formula. The third one, dy dx is equal to 2y. So in this case, our observation would be that the slopes only depend on the y value. And so if we look at that, when y is 0, the slope is 0. When y is 1, the slope's 2, so then it gets 4. So they should all be parallel when the y's are the same. Okay, and if we drew like a general solution, if we look at this, if I follow kind of along the curves, a general solution would be something like this. And so if we think about what a curve that makes, the original equation would be an exponential function. Okay. And we can also, from slope fields, tell asymptotes. And so when we get all the slopes to be 0 at a certain y value or a certain x value, we get an asymptote. So if you kind of look at this, how I drew it, either if I draw it above or if I would draw kind of below, it would follow that there is going to be an asymptote at x or y equals 0, or the x-axis. Okay, so we have a horizontal at y equals 0. Okay, because here wherever we draw our slope field, our general equation, like if I know my point is 1, 1, and I trace along, I'm still going to level out at 0, and it's never going to cross. So when you have a slopes of all 0 or all undefined, you get an asymptote. If the slopes are all 0, then you have a horizontal asymptote. If you get the slopes to all be undefined, then you get a vertical asymptote for the original function. So down here it says this is a slope field. The line segments indicate the direction the solution curve is heading. And if you follow the direction of the curves, you can draw a solution to the differential equation at specific points. And without solving a differential equation, you can get an idea of what the graph of the original function looks like. So slope fields also allow us to solve differential equations graphically and determine certain characteristics of the original equation, such as asymptotes, if we can't find it algebraically. So if we look at number 3, it says graph a particular solution to the slope field through the point 0, 1. So I'm going to start at 0, 1, which is here. And what it says is for graphing a particular solution, we start at the point they gave you, which is 0, 1. And the graph should be parallel to the slope lines and be some sort of average of the slopes if it goes between the lines. And the goal is not to hit every slope. Okay, you don't have to hit them. So like here, my slope is 0. So that means I'm going to start flat. But as I move to the right, we're like between this slope here, the one I'm highlighting, and still the 0. So it's going to start curving up because of this one. It's kind of an average of these two that it's in between. So I'm going to keep going. So you have to draw these very slowly. And you don't necessarily have to hit them. So this one I'm about to hit, I'm going to go steeper, so I'm going to go parallel to it. And then I'm going to keep going, and I'm going to be parallel to that. Okay. And then my left side should look similar to the right because the slopes are the same. They're just in the negative direction instead of the positive. So this one I'm going to start leveling out, and then because of this slope, I'm going to start going up. Going up, I'm going to stay parallel to it. And then I'm going to stay parallel to the other one. Okay, and if it goes between it, you kind of average it. So do the best that you can on these. I'll be looking for more general shape and that you follow along the path. And then the last question on here and that we're going to do today is an application question with it. So for number 4, it says, for which of the following differential equations will the slope field show nothing but negative slopes in the 4th quadrant? So if I think about the 4th quadrant, we know the signs are positive, negative. So when we want to think is when I plug in a positive x and a negative y, what would be my slopes? So the first one is negative x over y. So if I plug in a positive x over a negative y, I get a negative over a negative, which is a positive. So for the 4th quadrant, we would get all positive values. So A is not our answer. For B, xy plus 5. So I would get a positive times a negative plus 5. So I'd get a negative value plus 5, but it depends if this negative value is bigger than 5 or less than 5 if it's negative. So at like 1, 1, at positive 1, negative 1, we would still get a positive slope. So that does not work. Xy squared. So if I do this, I get a positive. If I square the negative, I'm going to get a positive minus 2. And then again, because we're subtracting 2, it depends on the value. Like if I do 1, 1, I would get a negative slope. But at like 3, 4, I'd have 3 times 16, which is way bigger than 2. So I'd get a positive slope. So that doesn't work because we're looking for all negative slopes. X cubed over y squared. So x cubed, I'd have a positive cubed, which is a positive, over a negative squared, which is a positive. So these would be all positive. So that doesn't work. So it has to be E, but let's check it. So I have dy dx is equal to y over x squared is what it should be. So when I do that, I'm going to have a negative over a positive minus 3, which is a negative minus 3, and a negative value minus 3 is still going to give you a negative value. So that's why it's E, the slopes in the fourth quadrant. So that's kind of an application problem. So tomorrow or whenever we have class next, we're going to practice a lot more with slope fields, but this will give us more time to practice in class since you watched the lesson.